All right. Thank you all for the invitation, and thank you, Max, for organizing this. Right, I've been asked to speak today about this recent paper that I wrote with a fantastic group of collaborators, Cliff Chung at Caltech, and three amazing students, Francesco Callisto and Michele Turchini at Caltech, and Francesco Sciatti at Barcelona. So we'll be interested in understanding the completeness hypothesis, uh, not as some top-down statement from string theory, but actually as a consequence of self-consistency of scattering in a weakly coupled theory that has gravity. Uh, so using quantum field theory tools to understand a statement from the swampland program. So just a few words of introduction. Basically, the completeness hypothesis is asking a really fundamental question that has guided physics for hundreds of years. What is everything made of? And of course, experiment is, as always, the ultimate arbiter, and nature can and does surprise us. But we've seen over many decades that mathematical consistency also imposes what at times are surprisingly strong limits on what can exist, even in principle, within some paradigm like quantum mechanics or special relativity. Going back to Wigner's bounds on erupts of the Poincare group, just coming from unitarity and special relativity, and over the years, developments in quantum field theory and scattering amplitudes, understanding that gauge theory and gravity are unique and bootstrappable as the unique interacting massless spin 1 and spin 2 theories at leading order, the famous statement about no higher spin massless states, etc. Now, all of these concern what is forbidden. Asking if we can prove that something is required is much harder. But perhaps nature is maximalist, and that's, in a sense, what the completeness hypothesis is suggesting, that all charges permitted by Dirac quantization are realized by physical states. And I don't have to tell this group that the completeness hypothesis is totally central within the swampland program. It's this canonical idea, and it's motivated by all known examples from string theory, but it's also motivated famously by the absence of global symmetries in quantum gravity. If you want to break higher form symmetry, then you have to give Wilson lines a place to end, and the existence of all possible charges do precisely that, as famously shown. But in this talk, we're going to rigorously prove a version of the completeness hypothesis, as I said, using scattering amplitudes, particularly analytic dispersion relations. Now, before I do that, I should note that the version of the completeness hypothesis I'm going to prove in this talk is in some sense weaker and in some sense stronger than that which appears in the traditional no global symmetries argument. So in the usual swampland story, if I tell you that there's a fundamental in the spectrum, that's enough for completeness because one can always group together fundamentals. For example, take a black hole and throw a bunch of fundamentals in to produce any irrep of the gauge group or the symmetry group that you like. On the other hand, those are all multi-particle states, sometimes non-perturbative states. And in the argument I'm going to give in this talk, it will be weaker in the sense that I'm going to assume the presence of some seed charges. For example, I'm going to grant myself the existence of fundamentals in the spectrum. But from this, I'm going to derive something much stronger than the traditional completeness hypothesis. I will derive the existence of one particle state, single particle states of every possible charge from bottom-up reasoning. So the main workhorse of this talk will be a so-called subtracted dispersion relation. I have some 2 to 2 scattering amplitude. I divide by some power of the center of mass energy, and I do some contour integral around the origin to define this object Cn of t. It's the coefficient of s to the n as a function of t in the low energy expansion of the scattering amplitude. So something totally standard from analytic dispersion relations, positivity bounds, etc. And then I can do the usual move of blowing up the contour to be some integral over the S channel, some integral over the U channel, and some boundary term Bn of t. So now here's the basic idea. If we know for sure that we're in a situation where some Cn of t is not zero, but where Bn of t is zero. So where we're guaranteed some interaction in the low energy theory, and we're also guaranteed that that action or that interaction is unitarized in the UV, so it drops off epsilonically more quickly in the UV than in the IR. Then we're guaranteed that there has to be some state in either the S channel or the U channel to make that happen. And that is literally the only ingredient. So, what interaction can we look at that guarantees this behavior? Well, happily, quantum gravity provides exactly this situation. All pairs of particles, by definition, interact gravitationally. So any 2 to 2 elastic scattering has some component in the IR that goes like g Newton s squared over t. So C2 will not vanish as long as there's non-zero Newton's constant. C2 will be just 8 pi g over t. And it's also been argued from famous general causality and unitarity reasoning that gravitational scattering should scale slightly more weakly than s squared in the UV as long as t is negative. And this is also satisfied by all known string examples. You can think about the amplitude Reggiizing to s to the 2 plus t. So under very general assumptions, we have that B2 vanishes for a theory containing gravity. So our dispersion relation here has just become that 8 pi g over t equals a sum over the discontinuity in the amplitude in the S channel or in the U channel. So there exist states in either the S or the U channel as soon as you posit that you have gravitational scattering that's unitarized. So nothing controversial so far. But a unique thing about gravity is that unlike in field theory, any weakly coupled UV completion of GR has to be done at tree level. This is not the case in field theory. For example, if I were to take quantum electrodynamics and integrate out the electron at one loop, I have some EFT with f to the fourth interactions, the so-called Euler-Heisenberg Lagrangian. That's completed that weak coupling, but it's completed at one loop level. In gravity, on the other hand, it has to be more Higgs-like. There has to be an exchange of tree-level states. And the reason we gave 10 years ago now is a basic H-bar counting argument. Any completion that remains weakly coupled from low energies to high energies has to have some well-defined H-bar expansion by definition. Diffeomorphism is a classical idea and so has to be at order 1 over h bar. And in gravity, unlike in usual field theories, the interaction terms are uniquely fixed relative to the kinetic term. If you just act with diffeos on the kinetic term, you generate the h mu nu cubed, h mu nu to the fourth, etc. terms in the IR. And so these are, by definition, also order 1 over h bar. And so the 2 to 2 scattering amplitude is order 1 over h bar. And so if there's a consistent weakly coupled completion, it also has to be order 1 over h bar and thus tree level. And of course, this is also true in string theory as well, where graviton-graviton scattering is unitarized by the exchange of some tower of states at tree level. The amplitudes are meromorphic. And so we're going to take this as our assumption that we have a weakly coupled completion. So all of the states whose existence we derive from that dispersion relation a few slides ago here will be single particle states. Okay. So now let's talk about symmetry. We want to assume that there's some symmetry group G. We'll take G to be exact in the weak coupling limit. Maybe it's a gauge symmetry. Maybe it's some exact symmetry in the low energy theory that's broken non-perturbatively. That won't matter. But what we'll be interested in is the maximal abelian subgroup of G, which we'll call H. So this is the Cartan subgroup. It's a bunch of copies of U1. And we're interested in the charge lattice, the Cartan charge lattice of the group. So the idea will be to posit some set of particles in the spectrum, for example, fundamentals of G. We'll scatter them to deduce the existence of new states via analytic dispersion relations. And then using those newly deduced states, we'll scatter over and over again and repeat ad infinitum. And this process is not guaranteed to close. But if it does, and if we deduce the existence of single particle states populating the entire Cartan charge lattice of H, we'll say that the theory exhibits charge completeness. And as I mentioned, gravity plays the central role in guaranteeing the existence of these new states. We had to have that G Newton is non-zero in order to guarantee that there are states in the SNT channel, or excuse me, SNU channel. So, any questions before I describe the algorithm we'll use to prove completeness? Okay, hearing none, uh, I want to say a few words about group theory that will be relevant to this talk. So we will define the set of eigenvectors of H as spanning some lattice lambda, which will define the set of abelian charges, also called weights. So here's some example in some uh, case where the Cartan subgroup is two-dimensional. And we'll posit that there's some initial set of charges guaranteed to be in the spectrum. We'll call this Q here in orange. So for example, we always have the graviton by definition, so Q will contain the singlet, but we'll also assume that the group isn't just totally trivial, that there's some state that's charged under the group. And the spectrum has to be invariant under the action of the group just by definition, since G is supposed to be a symmetry. So acting on Q with G is supposed to reproduce Q. And furthermore, if there are any outer automorphisms, for example, charge conjugation, then acting with C also has to reproduce Q. And using these moves will be really crucial. So just a few other ingredients for terminology. We'll talk about roots quite a bit. So these are the eigenvalues of the Cartan subalgebra, and you can think about them as corresponding to moves between weights, between charge vectors in the lattice. We'll talk about the Weil group quite a bit, which describe the isometries of the root system. So these allow us to reflect charges through a plane in the Cartan lattice orthogonal to a root. And you can think about the roots as describing raising and lowering operators. So for example, if we were talking about SU2 or SO3, where the symmetry is like that of angular momentum, the Cartan lattice just describes, in that case, the set of z values of the angular momentum, SZ. And there, the roots would literally be the raising and lowering operators. And so what will be an interesting concept for us to use is the notion of Weil strings. So this is the idea that if you have some charge in your theory, you can figure out what are the other charges that are guaranteed to be in the same irreducible representation as that particular charge. So, for example, if we have some charge q in the lattice, then q plus kr for r a root and k an integer in some range that's defined geometrically is also guaranteed to be in that same irrep. So if Q is in big Q, then Q plus R is in big Q. And so we'll use that to guarantee that our set of charges is invariant under the action of the group, and given one charge, derive the existence of other charges. And so you can sort of see where this is going. If we have some set of charges in our charge lattice, we can deduce the existence of more of them depending on what our group is. And so, as you might expect, non-abelian symmetry will play a big role in the rest of this talk. The one other concept I want to remind you of is the so-called center of the group, which are the elements that commute with every element of G. So representations that have the same charges under Z are in, we say are in the same central charge sector, which occurs if and only if the weights can be connected by integer combinations of roots. So what we'll need to start with is some state in every single central charge sector in order to hope to get completeness, just because you can't connect states in different charge sectors via the roots.
I have a question.
Yes.
The second last point on the previous slide was that weight strings or Weil strings, because you said Weil strings, but it says weight strings.
I meant to say weight strings. Yes.
Okay, okay,
Um,
thank you.
yeah. The example of this you should have in mind is, again, going back to angular momentum and SU2 or SO3. If I tell you there's a state with SZ equals, say, 3, then you know that all the states with SZ minus 3, minus 2, minus 1, 0, 1, 2, 3 are in that same irrep. And this is the multidimensional generalization of that notion of raising and lowering operators and what's the range which you can act with the lowering operator and remain within the same irrep.
Okay, thank you.
All right, so here's the idea. We're going to do two to two particle scattering, elastic scattering. So Q1 and Q4 have equal and opposite charges. Q2 and Q3 have some other equal and opposite charges that are inside our group. And we're choosing them in this way such that the T-channel state is neutral, so the graviton is guaranteed to contribute to the dispersion relation. So we have a guarantee of states in the S and U channels. So we either have Q plus Q prime in our spectrum or Q minus Q prime by virtue of the dispersion relation. So we'll write this logical deduction as follows. Q tensor Q prime gives us Q plus Q prime or Q minus Q prime. And by CPT, of course, all the opposite charges are present too, but that won't be important. But the problem is that we don't know which is in our spectrum. Um, if both of these are not in our original spectrum, that means our original spectrum is not sufficient to describe the dispersion relation. And so we have to add one or the other of these charges. And in that case, we call the process conclusive. On the other hand, if either of these states is in Q, then we can't conclude that the new states are in the spectrum because we don't know that both the S and U channels are turned on, and we call such a process inconclusive. Now, for a conclusive process, we have to update Q. And so we have to figure out whether we need to add Q plus Q prime or Q minus Q prime. So what we do is we check the entire orbit of both of those charges under the action of the group and any other automorphisms to see if we can map Q plus or minus Q prime onto each other. And if we can, we automatically get to add both of them and their full corresponding irreps to Q. If they're not related, then we have to consider both options and repeat in a sort of decision tree and see if the algorithm closes. And in some cases it will, and in some cases it won't. But if it never halts, and if we can conclusively establish that Q equals the full charge lattice lambda, then we've proven charge completeness. So as you can see, it's sort of a game where we have some set of moves allowed to us in the lattice. They're prescribed by the Weil group, by the isometries of the roots inherited from the symmetry group G. And so depending on the symmetry, we have a different set of moves. And so we have to see whether we can reach every point in the lattice by scattering over and over again and orbiting the charges around. So let's first try this for an abelian symmetry group. So we have just G and H are both U1. Our starting spectrum is just a graviton, an electron, and a positron. And for graviton-electron scattering, both of the deduced states are in Q already, so it's inconclusive. On the other hand, for electron-electron scattering, we conclude that there's either a state of charge -2 or a state of charge 0. But 0 is in Q already, it's the graviton, and we don't know that both the S and U channel are turned on. Could be that just the U channel is present here, and so it's again inconclusive. So the algorithm fails for a single U1. For multiple abelian factors, the story is largely the same. If we give ourselves a starting spectrum of the graviton, an electron, and positron, and their dark components under the new U1, we can try the same thing, but scattering with the graviton is inconclusive. But we find that scattering an electron and a dark electron, we conclude that there is some state not in the initial spectrum. One of these has to be added, but we don't know which one. And at the next step, all the scattering pairs are inconclusive. There's always a state already in the spectrum that one can pick out, and the algorithm fails. So we somehow need more moves available to us within the lattice, so this suggests we should look at non-abelian symmetry. So let's try the simplest non-abelian symmetry group, SON. So just to remind you, for SON, the Cartan subgroup is the floor of n over 2 copies of U1. And the charge lattice is very simple. It's just the integer grid on that space of U1s. So very, very simple charge lattice. SON has a non-trivial center. If n is even, the center is Z2. And so we have two charge sectors, central charge sectors, which are just given by adding up the charges mod 2. So for SO3, we don't have any better luck than for U1. The root system just comprises raising and lowering operators. The lattice is just the integers, and the Weyl group just swaps the highest and lowest weight states in each representation. So we find it running through the algorithm, we don't have any rich structure. It works exactly as in the U1 case, and it fails as expected. So what about more non-abelianness? So SO4 is better. So here we have two copies of electromagnetism. The charge lattice is z squared. And the Weyl group describing the isometries of the roots just comprise the sign permutations of even signature, so either swapping entries or multiplying by an overall minus sign. So let's take as our initial spectrum just the graviton and the fundamental and see what we get. So we scatter as before, and we either get a state of charge -1 -1 or -1 +1. And if we orbit this through the Weyl group and the lowering operators, we either have a new S-channel state here or a new U-channel state. But what these describe are the two-form representations that are either self-dual or anti-self-dual of SO4. But it's possible to have one without the other, so this is inconclusive. We don't know, again, that either the S channel or the U channel is turned on. It could be one or the other. But we got close there. So we just need a little bit more information. So remember, SO4 is like SO3 squared, and it admits an outer automorphism that swaps each factor. Another way to say that is I could upgrade from SO4 to O4. Now the Weyl group is just slightly bigger. It comprises all signed permutations. And our previous SNU channel states are in the same orbit. They're in the same irrep of O4. So the algorithm is conclusive. So just starting with this initial set of states here, the fundamental in red and the singlet, the graviton, in black, and running through the scattering algorithm and continuously applying this outer automorphism, or if you like, continuously doing some O4 rotation, we find the following. So just scattering two fundamental charges gives us all the states in orange. Rescattering two of the states in orange gives us the states in yellow here, which is the fundamental multiplied by a factor of 2. Rescattering those gives us the states in green. And continuing and always orbiting through the full Weyl group, we get some set of growing squares in factors of 2. We'll call these ultra-charged states. So eventually, we can make this square as big as we like, and then I can use lowering operators, the roots, in the weight strings to reach all the states in the z equals 0 charge sector, which is in black here. So all the dots in black, I can reach everything within this square. But of course, that square was arbitrarily large. I can take little n to infinity, just run this algorithm an infinite number of times, and I get the full z equals 0 central charge sector, just as a consequence of consistency of analytic dispersion relations and the existence of gravity. But then, given one of those ultra-charged states on the corner here, I can scatter against the fundamental, and I reach the z equals 1 sector as well, the dots in gray. And I can run this same algorithm, and I just have some square that's been slightly tilted, shifted by 1 unit, say clockwise in every direction. And so I get completeness of O4. So the first non-abelian symmetry group for which we can derive completeness in among all Cartan charges just as a consequence of consistency of scattering amplitudes. And again, all of these states, these super highly charged states, have to be single particle states, which is another consequence of consistency. So what about other SONs?
I just had a quick
Yeah.
question. Um, in these states that you're generating that have the new charges from the initial C charges, is there
Yeah.
any assumption on like the width of these resonances? Like, are you assuming that they're like infinitely peaked or like very sharply peaked so that it's like well defined to like put them back into the S matrix? Like,
Yes, yeah, we're assuming that in some in a weak coupling limit, the UV completion of gravitational scattering is meromorphic, which is a consequence of that H bar counting argument I gave earlier. So here, all the amplitudes are assumed to be meromorphic in the weak coupling limit, so that we can take these states that we derive inside the amplitude and take them as external states. A
Okay.
way to think about that is, think about amplitudes in string theory, like the heterotic scattering amplitude computed by Gross back in the day, or indeed Virasor-Shapiro. Gravity in all these cases is given to you by is completed by some infinite tower of
Yeah, there it's infinitely peaked, and yeah, no, that's a little less, yeah. But okay, thanks.
it would be nice in principle to talk about, what happens if I start going to finite coupling, where things get finite width and all that. I'll have nothing to say about that in this talk, but that's a future direction, I guess.
Okay, thanks.
Um, so we saw SO4 didn't have quite enough non-abelianness to generate completeness, but when we enlarged it to O4, it did. So what about higher SONs? So for SO5, we have the exact same set of charges. Lambda is just z squared, but the Weil group is bigger for SO5. The Weil group is all signed permutations, exactly like O4. So the immediate consequence is that completeness of O4, just given the singlet and the fundamental, so given the graviton and the smallest state charged under the group, immediately implies completeness of SO5, starting from the fundamental and the graviton. So just trivially. So now we're ready to tackle the general SON case for n bigger than or equal to 6. So remember, we have floor n over 2 copies of electromagnetism. We just have the integer charge lattice, and so we can proceed by induction. The case of n odd is pretty simple. So we assume we have the graviton and fundamentals of SON, which imply that we have the charges associated with the singlet and the fundamentals of SON minus 1 within our lattice. And so by the inductive hypothesis, given the singlet and fundamentals of SON minus 1, we have SON minus 1 completeness in that sublattice. Uh, so, but remember, SON minus 1 and SON have the exact same Cartan subgroup and charge lattice because of this floor function. So we have completeness of SON trivially for n odd. N even is a little more tricky. Uh, so completeness of SON minus 1 means that we have all charges of the form Q1, Q2, all the way up to Q n over 2 minus 1, comma 0, along with all their permutations for all integers Qi. And so we can choose these two charges, Q1 through Q n over 2 minus 2, with zeros in the last two entries, and scatter against the state with all zeros in the first n minus 2, n over 2 minus 2 entries, and arbitrary integers in the last two entries. And we get the following alternatives depending on whether we have states in the S channel or the U channel. But the Weil group now contains all signed permutations for n even, and so both charges have to be present, and so the algorithm is conclusive and we have completeness. So we have completeness now for all SON for n bigger than or equal to 5, and also for O4, just given the singlet and the fundamental. So now it makes sense to start asking about other groups. The gauge groups that are probably the most interest in particle physics are SUN. So let's talk about SUN. We have a larger Cartan group. We have n minus 1 copies of U1. And things will start to get a bit more complicated now because we don't just have the simple integer lattice that's totally orthogonal. Instead, we have an integer lattice multiplied by these vectors mu I that we call the fundamental weights, which are not all orthonormal. But this isn't too exotic. Remember, in the standard model, the structure of SU3, flavor, and isospin, one has these triangular charge lattices, famously. And that's a consequence of this non-orthogonality of the fundamental weights. So just keep these familiar pictures from the particle data book in the back of your mind in the rest of the SUN discussion. So what we're going to do, we could, of course, laboriously write out charge vectors in terms of this orthonormal basis, but instead, let's just label the charge vectors by their Dynkin coordinates, by their multiplication by the mu I basis. So we have a non-orthogonal basis, and we'll just have to remember to be careful when handling dot products. In this basis, the roots take this very nice form, and the action of the Weyl group is pretty simple. If I have some Dinkin labels for some charge state, and I want to reflect through some root, Ri, all I have to do is flip the sign of the ith Dinkin coordinate, and then add it to its two neighbors. Charge conjugation is also really nice in this basis. It's just reversal of the full set of Qi labels. All right, so given all that background, let's see if we can actually prove charge completeness for SUN. Well, we might expect trouble because for SON, the center was either trivial or Z2. So it wasn't too hard to get every single charge sector just from the graviton and the fundamental. But for SUN, we have a non-trivial center symmetry. We have a Zn center, and we have n different central charge sectors. For SU3 in the standard model, this is called triality. It was discovered decades ago. And for SUN, we can call this n-ality. So the roots move us among states of the same n-ality. The fundamental and anti-fundamental have n-alities 1 and n minus 1. So we at least expect to need more states than that to get completeness. We should expect to need states of every single central charge sector as in our seed to get completeness. So for SU3, for example, as I said, we have three central charge sectors here labeled in black, green, and purple. And the fundamental and anti-fundamental have z equals 1 or 2, here shown by these triangles. The octet, again familiar from particle physics, is this black octagon plus the center. The decouplet, either the 10 or the 10 bar, is this brown or gray triangle, etc. And we can label the central charge sectors for these various objects, so we expect to need something in every single central charge sector. So if we try with just the singlet, the fundamental, and anti-fundamental, we at least have a state in every charge sector, so we can see if we run our algorithm and get completeness, but one immediately finds that the algorithm is inconclusive. There's not enough non-abelian symmetry to bootstrap your way out to every single charge if you don't know whether the S or U channel is activated. But we can do a little better. If in addition to the graviton, the fundamental, and anti-fundamental, we add the octet to our initial set of charges. So then we can scatter the following choices of states, and we act with Weyl transformations and charge conjugation after each step to generate these new states on the next line. One finds that the 15 and 15 bar have to be present as well. So bigger triangles, so sort of rescaled versions of the 3 and 3 bar. And so given this observation, you can iterate and you do actually find completeness from this initial choice of spectrum. You end up being able to bootstrap your way to any state in the lattice. If instead of the octet, if instead we take the 1, the 3 bar, and the decouplet, and do the following scattering, then we wind up with a rescaled version of the octet. We get the 27. And we can construct an algorithm to get bigger and bigger hexagons, and eventually we cover every state in the z equals 0 charge sector, and then scattering against fundamentals or anti-fundamentals, as in the SO4 case, generates large reps with z equals 1 or 2. And we can iterate this and keep repeating this algorithm arbitrarily and find completeness for SU3. So again, for SU3, we just needed to add either the octet or the decouplet to get completeness. For SU n bigger than or equal to 4, as I said, our choice of spectrum suggests we should have some state in each of the central charge sectors. And for SU4 and higher, that alone is enough to guarantee completeness. One state in every single central charge sector. And we can see this as follows. So recall the roots and the action of the Weyl group, and just take the following states in the adjoint. So let's assume we have the adjoint, scatter R1 against R3. We get the following two options. These are related by the action of W3. So I have both of these in the spectrum. I scatter them against each other. And these two options in the SNU channel are also related by some string of Weyl group reflections. So these are both in the same irrep, or they're both in the spectrum. And so we have some rescaled version of the adjoint. And if we do this n times, we get a 2 to the n rescaled version of the full set of adjoint charges after orbiting through the full Weyl group. So this is directly analogous with the SO4 construction. Remember the big purple square earlier. And so we can act with lowering operators to generate all the z equals 0 states within the polytope. And so we get the full z equals 0 charge sector. And now how do we get all the other charge sectors? Given any state in, say, the z equals k sector, I can obtain the fundamental weight mu k via lowering operators, just trivially. So now let me scatter this state against this particular choice, which is in the z equals 0 sector, which exists within our theory by completeness, which we've just proven in the z equals 0 sector, just given the adjoint. And so doing this scattering process, we get either a state that's highly, highly charged and is arbitrarily large in either the z equals k or z equals n minus k sector. And for either case on the right-hand side, one generates via lowering operators either the entire z equals k sector or z equals n minus k sector. And whichever option you have, the other option is guaranteed to be there via charge conjugation. So we get completeness in that way, just given the adjoint, the fundamental, and any single state in all the other central charge sectors. So that's the story for SUN completeness. So I now want to move on to more exotic groups, but I'll pause here and see if there are any questions on the construction so far. Okay, hearing none, let's do the next sort of the least complicated generalization, which is the spin group. So the universal cover of SON. This is very familiar to you from angular momentum. The fermions are in the spin group that generalizes the SO representation of Poincare. So you can think about this as some internal quantum number that looks like a fermionic spin. This exists in string theory. There are spin 16 factors that occur in various string theories. So it has the exact same roots and the same Weyl group as SON, but an enhanced charge lattice because we're now allowing integer and half integer quote quote angular momenta. So here, this is all very familiar. Lambda 0 is the integer lattice of integer spins, and lambda 1/2 is the lattice of half integer spins. So we should take our initial spectrum, our guaranteed seed spectrum, to comprise the smallest faithful representations of spin n. So we'll take the vector and the tiniest spinners. And for our scattering algorithm, we're already guaranteed completeness of the SON subgroup of the lambda 0 charge lattice, just trivially. And so what I'll do is I'll take the ultra-charged corner states, the states on that big purple square, generalized to n dimensions, and scatter them against these small spinners. For example, for spin 4, I can scatter against 1/2, 1/2. And so what I get is I get a deformed big orthant where all the vertices have been shifted by 1/2 in various directions. And from these vectors in lambda 1/2, I can orbit them inward using the lowering operators, and I cover automatically the full interior of the half integer sublattice. And since I can take little n arbitrarily large, I have completeness of spin n just as a consequence of SON completeness. So we can walk through various other Lie groups to see what it takes to generate completeness. The symplectic groups will be particularly nice. Symplectic group SPN you can think of as just a set of linear transformations in an even number n dimensions that leave the symplectic form shown here invariant. For our purposes, the full-blown structure of SPN won't be important. We'll just need the fact that its charge lattice is exactly the same as SON. It's z to the n over 2. And the vector of SPN has the exact same charges as the vector of SON. But of course, SPN is not the same as SON. It has a different root system. But happily, its root system contains as a subset the root system of SON. So SPN has exactly as many moves available to us as SON, plus even more. So we can play the same game for SPN as SON. It's an immediate consequence of its completeness is an immediate consequence of SON completeness. So finally, let's talk about E8. Now, I won't go through all of the exceptional Lie groups, that would be laborious, but E8 is interesting given its importance in string theory. It famously shows up as one of the gauge groups of the heterotic string, E8 times E8. Now, for E8, unlike the lesser Lie groups, the adjoint is actually the smallest non-trivial representation, the 248. Uh, the full structure of E8 won't be relevant for us here, but what we'll need to know is the lattice of charges and the lattice of roots. And for E8, these are actually the same. The E8 lattice is famously self-dual. So its set of spacings among charges is equal to the set of charges themselves. And you can think about the lattice as just lambda 0 combined with lambda 1/2, where lambda 0 is some orthogonal integer charge lattice such that the sum of charges is an even number. And lambda 1/2 is some half integer charge lattice, again, restricted such that the sum of charges is an even number. And the root system, the minimal set of roots that generate the full lattice, are just plus or minus EI plus or minus EJ with independent signs, and R1/2, the set of all points in lambda 1/2, with each charge component having magnitude 1/2. So we'll use these root systems. And our initial spectrum we'll take is just the graviton and the adjoint, the 248. The graviton is automatically there because we're talking about a theory with gravitational scattering, and we're just taking the smallest non-trivial representation of the gauge group. So the adjoint has the set of charges equal to the root system. That's always the case for any Lie group. But we recognize R naught here and lambda naught here as just the charge lattice and root system for the z equals 0 sector of SO16, which are generated by our scattering algorithm if we start from the adjoint. So just running through our usual SON construction, we are guaranteed that we have to append to Q, append to our starting spectrum, the full lambda 0 part of the charge lattice. So we have all of those states automatically as a consequence of gravitational scattering. In particular, this point, which is by definition in lambda naught, 2 to the n times E1 plus E2, which we'll call Qn, is in lambda naught, and it's therefore in Q, our spectrum. And the Weyl orbit of Qn, orbiting through all the roots, comprises precisely the E8 adjoint weights, R naught and R1/2, rescaled by a factor of 2 to the n. So all of these points are in Q as well, and you might see where this is going given our other constructions. So now we have some 2 to the n rescaled version of the adjoint, and using lowering operators, we get all the points in the whole charge lattice that are contained in this polytope. And since this conclusion holds for n arbitrarily large, Q equals lambda, and E8 is complete. So to say that again, just given the graviton and the adjoint of some exact E8 symmetry, a consequence of analytic dispersion relations and assuming a weakly coupled completion of gravity is that there are single particle states of all possible E8 charges. And indeed, that's the case in string theory, but we're getting this entirely using quantum field theoretic input. All right. The final thing I want to say is a really cool observation connecting charge completeness with grand unified theories of the standard model. So if you think about SU5 guts, so this is a sort of old school topic, but just to remind you, the matter spectrum of the standard model, as we all know, looks kind of random, and why do we have all these gauge bosons? Why do we have all these quarks and leptons, etc.? But if I recall how these are embedded in an SU5 gut, the gauge bosons are in a 24 of SU5. The Higgs is in a 5 and 24 of SU5, and the quarks and leptons of the standard model are in the 5 bar and the 10 of SU5. So why would I have these representations? What's special about them? It turns out something is special about them from the context of our completeness algorithm. For our completeness story to work, remember, so we had Z5 center symmetry for SU5. And in order to guarantee completeness as a consequence of scattering amplitudes, we needed to start with a spectrum that contained a representative of each central charge sector. But this is precisely what is provided by the standard model field content. Z equals 0, 1, 2, 3, 4 are provided by the 24, the 5, the 10, the 10 bar, and the 5 bar. So an SU5 theory that was missing any quarks, leptons, or bosons of the standard model could not be proven to satisfy charge completeness using our logic, using analytic dispersion relations. So in that sense, all of the field content of the standard model is mandatory if you want to infer charge completeness, which is amusing, I think. And what's cool is the same exact thing applies to SO10 guts, or more precisely spin 10 guts. In that case, the gauge bosons are in the 45, the Higgs is usually in the 10, although there are other options, and the quarks and leptons are in the 16. And the center symmetry of spin 10 is Z4, and each of these irreps precisely provide a representative from each central charge sector. So the field content of the standard model provides exactly what is needed, nothing more than nothing less, to guarantee charge completeness using analytic dispersion relations, using our logic. So that's I think an interesting and suggestive connection here between guts and the completeness hypothesis. So just to kind of remind you the basic ideas here and what we'd like to do in the future, uh, this talk involved really simple ingredients. We posited that there is some non-abelian symmetry in the spectrum of the theory. Uh, it could have been gauged, could have been a global symmetry that's exact at tree level and broken non-perturbatively. We assume that there's some set of particles charged under that symmetry, so that the symmetry isn't just totally trivial. And we asserted that gravity exists and is completed in a weakly coupled manner. So each of these very innocuous hypotheses leads to some particular consequence in the context of analytic dispersion relations. That is, assuming that there's some non-abelian symmetry, we were able to manipulate the charge vectors via the Weyl group and raising and lowering in order to relate the states that we inferred in either the S or the U channel to each other and then take the new inferred irreps outside and rescatter them. And given that gravity exists and has a weakly coupled completion, we were able to use tree level amplitudes and guarantee that the S or U channel exists via a subtracted dispersion relation, which was non-zero due to the fact that we had the G Newton over T, the Newtonian 1 over R potential in the physics of the theory. And all of this led us to a very strong conclusion that in case after case, we found that the entire Cartan lattice of charges is fully populated by single particle states, so a version of the completeness hypothesis. There are, of course, a lot of things we're interested in doing in the future. The fact that we got such a strong conclusion mechanically via very general QFT amplitudes methods suggests that there are potentially lots of options in the swampland program amenable to investigation in this way. Right now, we're working on proving completeness instead of in the Cartan space of charges among all irreps. Those are not quite the same statement. It is possible to span all Cartan charges without having literally every single irrep of the group present, but we think we can actually prove completeness among irreps, which is much, much closer to the standard swampy version of the completeness hypothesis. Also, as we saw in this talk, whether the gauge group or whether the group G was gauged or global wasn't important. It would be nice to find a way to make whether it's gauged or global play a role and connect it to the weak gravity conjecture. And indeed, even though gravity played a central role, really something slightly weaker than gravity was necessary. We just needed an analytic dispersion relation that was guaranteed to be non-zero in the T channel for all elastic scattering processes. So we needed some force that coupled to all states, but we didn't need universal coupling. That coupling just had to be non-zero. So maybe it would be interesting to add some dilatonic exchange and see what happens if we weaken the presence of gravity. This question was asked already about fattening the width of these resonances. It would be nice if we could extend this to loops and multiparticle states, although it sort of trivializes if you allow multiparticle states. A big elephant in the room is we didn't make use of unitarity at all, which is sort of surprising because I drew that contour that one usually sees in the context of analytic dispersion relations and related some IR coefficient to an integral over the S and the U channels. But we didn't need that anything was positive. All we needed was that those branch cuts or residues were non-zero. It would be nice to add unitarity and connect this to positivity bounds and see if that strengthens our results. And there's just the sort of general open question of can we attack other swampland conjectures using amplitudes methods, the distance conjecture or other swampy statements. So thanks again very much. And yeah, please let me know if you have any other questions. Thank you.